Hey guys, it's great to be back with you. My name's Johnny and welcome to our section on analytical techniques. Before we even get started, I just want to kick off by answering the question that I'm sure you all have at home. Why do I even need to learn this? So, back in the beginning of time, when organic chemistry first started becoming a thing, scientists started running into an issue pretty quickly, which was, one, I'm designing all these cool reactions, all my test tubes are turning colors, but how do I know that the reaction is actually working? How do I know that I'm actually getting the right product? Two, when I go to buy my synthetic precursors, my benzenes, my acetaldehydes, all those molecules I need so I can make bigger things, how do I know that I'm actually buying the right molecule and I'm not just buying like a bucket of garbage? Well, these are questions that scientists needed an answer for relatively quickly. So they started developing a line of chemistry that we call wet chemistry, or sometimes called bench chemistry. These are literally the liquid reactions that you see those crazy professors do on TV. And they were originally just used to verify what molecules we had, okay? So here's a really common example. Tollens test. This is a reaction that you might recognize from organic chemistry lab. Or if you haven't seen it yet, you probably will at some point of the year, okay? And this is a common test, very classic test, that tests for the presence of aldehydes in a compound, in a solution, okay? Now, usually what we're trying to do is we're trying to differentiate, is it a ketone or is it an aldehyde? So what they do is they put the mixture into the test tube. Then they add silver oxide, okay? And that silver oxide, I'm not sure if you guys recall, is an oxidizing agent. So it's going to go ahead and add an oxygen to the aldehyde, oxidizing it. But most importantly, it's going to create a silver mirror that's going to precipitate out of the solution. And you're actually going to see that the walls of the test tube become silver. Pretty cool. So even though this sounds like a nice parlor trick to take home to your family, I'm going to explain why it's not really that useful. One, first of all, you need to have the reagent sitting around. You need to have that silver oxide in your lab, or you're never going to know if you have aldehydes, right? So that's already limiting. That means you're going to have to carry a lot of different reagents, okay? Two, it's not very reliable. It turns out that this reaction can actually work with some ketones. It actually could oxidize some ketones. So a lot of these wet chemistry reactions have exceptions. They're not really the most reliable tools. Third, and most importantly, it's not very specific. It doesn't tell me the exact type of aldehyde I'm getting. It just tells me, do I have an aldehyde or not? It doesn't tell me the length of the carbon chain. It doesn't tell me if there's two aldehydes, not one. It's literally very little information that I'm getting. So as hundreds of reactions were being developed every year, scientists needed a better way to know what molecules they are producing. Now, by the way, you might just be thinking, why not use a microscope, Johnny? Guys, remember, these molecules are so small that no microscopes, especially back in the day, could ever see what's going on at that level. Now we have electron microscopes that can see at a much smaller level, but still, that's not a good tool for confirming what molecules you have. So what is a good tool? Well, that brings us to modern methods of identification, or what we call dry chemistry, okay? So in general, these are going to be big, expensive machines that your university has spent millions of dollars on just to answer this one question of what molecule do I have in front of me right now, okay? So here's a good example of an analytical technique. It's called proton NMR. Okay, this is just one of the several analytical techniques there are. As you can see, it's such a big machine that someone can actually stand on top of it, all right? And you can imagine how expensive that is. And what it does is you put molecules in it, and it spits out this mess of peaks and troughs and spectrums and bumps and all this stuff. And as scientists, we are supposed to, right, scientists in training, we're supposed to be able to take this information and convert it into a molecular structure, okay? Now that might sound like a really hard thing to do, but you'd be surprised how much better it is to be looking at this kind of information than it is just to use a bunch of different test tubes and reagents to figure out what you have, because these peaks, these troughs, these spectras can give us a world of information more than you could ever get through wet chemistry, okay? So in this section, we're going to be going through some of these analytical techniques, and I'm going to be teaching you guys how to take crazy information like this and turn it into usable information that you can use either in your lab to identify what you have. Okay, that actually is an assignment you're probably going to have this year. You probably will have to identify a molecule based on NMR or based on IR, one of these analytical techniques. Or two, just to answer questions on your exam, because guess what? This is something your professors care about and they want you to be able to do on your exam. Okay, so that being said, that's kind of the intro. Let's go ahead and get more into detail on some of these analytical techniques.